Quantum mechanics has offered an explanation for how materials conduct electricity grounded in quantum principles. In solitary atoms, electrons occupy discrete energy states that follow quantum principles. When a solid state occurs and the atoms gather close together, Pauli's principle causes these discrete energy states to spread into energy bands. Now electrons can have different energy levels within their energy band. The highest energy band contains unfilled quantum states and is shared by all atoms in the solid, allowing electrons to roam freely across the material. This band is known as the conductive band. The valence band is the highest electron-filled band. There are no unoccupied quantum states in this band, hence electrons cannot move. The electrical conductivity of various materials is determined by the mutual position of these two bands. In conductors, the conduction band overlaps with the valence band, allowing electrons from the valence band to transition into the conduction band with no additional energy. These electrons become free charge carriers. When a voltage V is applied to a conductor, electrons collectively move towards a higher potential, resulting in an electric current. Metals are good conductors because their valence and conduction bands partially overlap. In the case of insulators, the conduction band is very far from the valence band, resulting in a large restricted zone between these bands that electrons from the valence band cannot cross. The insulator has no free electrons in the conduction zone and no free quantum states in the valence zone, hence there is no electrical conductivity. But the most exciting scenario concerns semiconductors. In these materials, the conduction band is significantly closer to the valence band. There is still a restricted zone, but it's far smaller than that of an insulator. At room temperature, electrons in the valence band can move into the conduction band if they receive enough thermal energy or energy from another source, such as being struck by a photon. Electrons stay in the conduction band for a very short time because there is a vacancy in the valence band and because each system strives to occupy a state with the least potential energy, they swiftly return to the next available position in the valence band. Nonetheless, in the conduction band, a certain number of free charge carriers are present at all times, while in the valence band, a certain number of free quantum states exist. When a semiconductor is coupled to voltage V, charge moves in a specific way. When an electron leaps into the conduction band, it creates a vacancy that is then filled by an adjacent electron from the valence band. Filling occurs in the direction of a higher potential, therefore the vacancies appear to be heading towards a lower potential. These vacancies behave like positive pseudoparticles, which we refer to as holes. Thus, the electric current in a semiconductor connected to an electrical circuit is made up of two types of free charges: negative electrons, which move to a higher potential, and positive holes, which move to a lower potential. A semiconductor remains electrically neutral because it contains an equal number of free electrons and holes. This electric current is quite feeble, since the mobility of electrons is determined by the number of holes in the valence band. At room temperature, this number is quite small. Semiconductors are the fourth group of elements on the periodic table, with silicon and germanium being the most commonly used. Each silicon atom in the valence zone has 4 electrons that form covalent bonds with the valence electrons of surrounding atoms. A semiconductor's electrical conductivity can be considerably affected if an element from the third group of the periodic table, such as aluminum, is put into a pristine crystal of silicon. Aluminum has just 3 valence electrons, hence many of silicon's valence electrons are unpaired. This causes an excess of unoccupied quantum states within the crystal, easily accessible by silicon valence electrons. The entire crystal remains electrically neutral. Only new quantum states emerge near silicon's valence zone. The extra atoms from the third group of elements are called acceptors, and this form of semiconductor is known as p-type semiconductor. Electrons from silicon's valence band easily move to the acceptor level, resulting in a large number of positive holes in the valence band, which serve as primary charge carriers in p-type semiconductors. Because the number of free electrons in the conduction band remains limited, we classify them as secondary charge carriers. If a fifth group element such as phosphorus with 5 valence electrons is introduced into silicon crystal, a new electron emerges with each phosphorus atom, leaving it without a partner to pair with. These electrons generate a new energy level near the silicon's conduction band, allowing newly injected electrons to easily enter the conduction band at room temperature. The number of holes in the valence band remains low, comparable to that of a pure semiconductor. This new energy level is known as the donor level, and the element that has been introduced, in this case phosphorus, is called the donor. An N-type semiconductor is created, with electrons in the conduction band serving as primary charge carriers and holes in the valence band as secondary charge carriers. The N-type semiconductor remains electrically neutral. If we connect these 2 types of semiconductors to an electrical circuit, an electric current begins to flow. The primary charge carriers in N-type semiconductors are electrons, whereas in P-type semiconductors, the predominant carriers are holes. Nonetheless, the electric current passes through both types of semiconductor. When we combine these 2 types of semiconductors to make a p-n junction, we get into a unique scenario. Even when the p-n junction is not connected to an electrical circuit, free electrons from N-type semiconductor rush to the holes in the p-type semiconductor. When electrons and holes collide, they recombine. The free electron merges with the hole and ceases to exist as a free electron, while the hole is filled with the electron and no longer exists as a free charge carrier. However, the formerly electrically neutral p-type semiconductor now has a hole deficiency, whereas the N-type semiconductor has an electron deficiency. The p side of this junction becomes negatively charged, and the N side becomes positively charged. This charge separation causes the creation of an electric field at the p-n junction, which, due to its orientation, inhibits the main charge carriers from passing further through the p-n junction. When the p-n junction is connected to an electric circuit, with plus to the p semiconductor and minus to the n semiconductor, an external electric field is formed, which opposes the internal electric field within the p-n junction. This reduces the internal field, which may eventually disappear, allowing primary charge carriers to flow through the p-n junction and generate electric current. If we reverse the battery's polarity, the external electric field will be restored, but in the opposite direction, from the N to the P type of semiconductor. The barrier between the P and N type of semiconductors increases even more as the internal and external electric field align in the same direction. This is why only the inverse saturation current passes through the p-n junction, which is made up of secondary charge carriers in semiconductors. We constructed a semiconductor diode, which is an electrical component that permits current flow in just one direction.